And we are going.
Hey everyone, welcome to our presentation. We are group 735X. I am Sam Rosshaven, and my other group mates comprise of Elijah Rice, Moises Castro, Jace Manning, Cameron Sarajadini, Brett Kniper, and Daniel Valencia. Here's our Hedgehog concept. If you don't know what a Hedgehog concept is, it is the intersection between your passions, your abilities, and the economic feasibility of your idea. And our Hedgehog concept for this design is to reduce barriers for scientific research by developing a product that may be assembled and maintained by a single layman through DFMA and standardized part sizes.
All right, so to give a kind of general overview of the design and some of the more general design choices. So kind of going along with that Hedgehog concept, one of the things we definitely focused on was minimizing the number of fastener types we used and the number of resultant tools that were required alongside the expertise of the user in order to assemble and maintain the shaker table. So if you can see the render on the left side of the screen, this is our full shaker table just without the kind of enclosure or shaker skirt that was present on the initial slide, just because it obscures things. But every single fastener on here, besides there are 2 hex nuts on the bottom of the linear rail and 4 for each sensor that are located on that shaker wall that's not pictured here, can be assembled with a single set of Allen keys. So it doesn't really require any mechanical know-how to assemble and make sure that someone that's like a lab technician would be able to put this together and maintain it pretty easily. And then kind of going along with that, for the fasteners for our well plate holder subsystem, so for our enclosure, we used wing nuts, which allow for the user to take their well plates out, clamp them in with their ODFI systems, and clamp in their test tube racks and whatnot, which is going to be the most interfaced part of the shaker table without the use of any Allen keys, just using their hands. So ideally, if this is inside of the microbioreactor, they wouldn't have to be taking this out in order to have enough light or have enough room to be interfacing with an Allen key when they can just use their hands. And kind of going into the overall design and how it interfaces with that microbioreactor. So we kept the overall design pretty lightweight and compact. The prototype itself weighs about 20 pounds, which is easy to move around as an individual person. It's pretty easy to wield as well. It's not like too big that it's difficult to grip. You can just pick it up by the sides and the bottom just fine. The overall size is 9 inches by 9 inches by 6.5 inches tall, and that is with that skirt wall around it. The base plate that you're seeing here on the left side of the screen is 8 inches by 8 inches. So we did manage to keep it fairly compact, which again is good because if you're putting it in the shaker table, you want to be able to move it around easily, and you could potentially fit more than one shaker table given the small size. Yeah, and then one kind of like some last notes here on this enclosure design for the well plate holder, to incorporate the ODFI. So one of the customer requirements was having visual clearance from the bottom of the well plate in order to integrate an ODFI system. So a lot of the ODFI systems we looked at were sized pretty similarly to a well plate, or within the size of well plate. So what we decided to do was use kind of like a peripheral clamp to hold our well plate in place. And when you put everything in, you would put the ODFI as the first layer, put in a Lexan separator that's about 1/16 of an inch thick. That's the profile of that enclosure wall. And that's to prevent any potential leakages or spillage from getting to the ODFI. And then you would place the well plate on top and use those wing nuts and that peripheral clamp to hold everything in place. And then we also designed our test tube rack to fit within that same enclosure wall and interface properly with that peripheral clamp. So you don't need to change that out at all to use those two different features. And the peripheral clamp also keeps the top of the well plate clear so that, with the microbioreactor, you can deposit the necessary media that you need and do whatever you need to do to the top of the well plate in order to have it work properly. And then as far as materials go, everything that you can see that's metal is made out of stainless steel. And this was to prevent corrosion, reactivity, porosity, and meet those BSL2 requirements. So just making sure that this isn't going to be holding any chemicals or media between experiments, that it can be cleaned properly. There's no reactivity so that everything can run smoothly and it'll be acceptable in that wet lab setting. Going more into our actual actuation. So this is the linear motor or the linear motion subsystem. So the way this is operating is we have this crank arm subassembly that has a crank arm, which is just a motor hub that interfaces with the shaft via set screw. And so this is rotating this arm that is attached to a block that is kind of linked with these carriage blocks on the linear rail via our orbital plate, or our plate that holds the orbital subassembly. So when this rotates, it has a diameter of 25 millimeters, which is pushing it in that constrained linear motion, total distance of 25 millimeters back and forth. And to give a better view of how this crank arm subassembly is working, one of the important things is minimizing the chatter, noise, and vibrations associated with our motors. As for the linear motion, we're going to be operating at 350 cycles a minute as our maximum. So we want to have that rod end bolt actuating freely, but we also want to keep the amount of clearance pretty low. So the way we did that was with a binding barrel, which is this white piece in the kind of direct middle of the screen. I don't know if you guys can see my cursor if I need to annotate here. Are you able to see it? My mouse?
No, I don't see it. But we see your mouse.
Okay. So yeah, so this binding barrel is just a bolt with female threads basically going through the middle of it, and it's the nominal size here is the same as this crank arm with this spacer with this rod end bolt, so that it's holding it all tightly, but it's not clamping down on it, which allows this rod end bolt to rotate freely and actuate with the attached clevis rod end to create that linear motion. Going into our orbital motion, so this is that orbital plate on the left that I was talking about, sitting on top of those carriage bolts, and this is the same linear attachment block that the linear motion assembly connects to that actuates that motion. But we have this NEMA 17 motor here on the orbital plate, and that's what's driving our orbital motion, which is moving in kind of a scrubbing pattern. So it's interfaced with a set screw, it's engaged with a set screw with the shaft. And then with the enclosure assembly shown earlier, there's a dowel pin that is fixed to that assembly that would drop into this flanged bushing And this is an oilite bushing, which is a bronze material. It's put there to prevent steel on steel wear. And when it experiences friction, it'll automatically lubricate that joint. So, the purpose of that is to prevent somebody who's unfamiliar with maintaining like lab equipment with lubrication from having to do that. So with these bearings, since they are self-lubricating, or these bushings, rather just preventing potential user error from causing the shaker table to fail before its lifetime is over. So that's what's driving it. And then looking at the linkages themselves, so these keep the purpose of these linkages is to tie the whole motion together, and prevent that hub from just rotating the plate on top. And the way these are assembled is with like a bushing case block here that has these same flange bearings inserted inside. And then those will interface with 2 shoulder bolts that'll allow for it to rotate freely and keep it constrained vertically so that there's not really any play. The shoulder bolts will keep it pretty secure, kind of like what was happening with the binding barrel, where it is not clamping it down, but it's keeping it very tight to minimize the vibration that's occurring on this plate. And then looking at the actual performance of each orbital pattern, or each pattern. So we were able to hit the customer need with our prototype of 350 RPM for the orbital motion, at a 25 millimeter orbital diameter, again using those linkages, which we kind of refer to as dog bones. With the linear motion and the double orbital motion, we weren't quite able to hit that with our prototype. And this is due to not having conservative enough calculations for our motor torque. So we could definitely swap out the NEMA 17 motor that's currently driving the linear actuation subsystem with a stronger motor, and then be able to increase the speed of our linear motion up to 350 RPM, which is currently acting as the bottleneck for not being able to hit 350 cycles per minute on our double orbital motion. And for anyone that's, I guess, unfamiliar with the double orbital motion pattern, that's like a lemniscate figure 8 infinity sign pattern. And basically the orbital motion is being achieved just with that NEMA 17 motor on the orbital plate. The linear motion is being achieved just with the linear driving motor on our base plate. And then the double orbital motion is using a control algorithm that uses both motors in order to achieve that pattern, using some dynamics equations. But talking more to the orbital diameter itself, since I know that's going to be a question that's brought up. So we do have a redesign that allows 4 different orbital diameters, specifically for the 10 millimeter orbital diameter. Since when we talked to the customer, something that we talked to them about like 3/4 of the semester, something that they spoke to was the fact that they really only use a 10 millimeter orbital diameter. We weren't able to implement this in time since we were already through most of the semester. And basically what it would require to keep both a 25 millimeter, which was the other orbital diameter that they were interested in, and the 10 millimeter orbital diameter, would be drilling a like mirrored hole pattern for that on our orbital plate. And then that would require us to swap our motors around, which would in turn require a redrill of the holes for the sheet metal holding up our linear rail system and our motors on our base plate. So a lot of additional holes that, if done initially, wouldn't really be much of an issue, but with the need for prototype testing in iteration, were kind of not feasible within the time span that we had left in the course. And then additionally, the other redesign that would be taking place is with these motor hubs. because you're switching from a 12.5 millimeter difference between the holes themselves for the bearing, for the bushing and the shafts. To prevent overlap of those parts, we would be switching to a base material with better wear properties like Delrin in order to achieve that. And then you would swap out those, and then you would swap out the orbital dog bones with those same like manufactured of Delrin linkages. And you could swap between those. But one of the last final note is that in a literature review we conducted, we also found that you could achieve empirically similar growth rates in cell cultures by changing the number of orbital cycles per minute in accordance with like a described proportion for the agitation rate. So this kind of has yet to be fully tested with outside of agitation rate. You also have to worry about the media and the way that it funnels and cycles through the well plate itself. But I think it's definitely promising that you could achieve not just the same agitation rate, but also keep the same pattern of frothing or like a vortex pattern in your well plates that you're trying to achieve with a different orbital diameters, achieve that same effect.
So here we have our enclosure, which is composed of PLA plastic and was made for the shaker table and designed for user safety, for hiding wires, and for providing a mounting area for the homing sensors. The enclosure was designed for user safety as it is tall enough to protect users from pinch points in the design, such as from the linear and orbital motion subsystems. Looking at the bottom right image, the enclosure also allows wires to run through the small gap created by the enclosure wall and the base plate, allowing for the wiring of the table to be organized and streamlined. Additionally, the enclosure is where the homing sensors are mounted to allow for choice on which side would serve as the linear homing slot and the orbital homing slot. As shown in the upper right image, the enclosure is secured through being clamped between the rubber feet and the base plate, with the screw threading through all of them. The enclosure was also broken into 4 separate pieces, one at each corner, and connected through tabs in order to fit and successfully print on our 3D printers. And next, we have a clip of the linear and orbital motions in action.
Let me know if I need to pause one of them for the bit rate to process. Or if it's just...
No, I think it's fine.
Okay, thank
you. For our user interface, we're using 3 perf boards and a rocker switch. So there's a stepper motor driver and sensor board that's hidden within the electronics housing. And then we have the control board and an LCD display board that are visible for the user to interact with. And then we have the rocker switch as well. We're pulling 12 volts of power from the wall outlet, and it's passing through the rocker switch to act as a hard power cutoff for any kind of emergency where we just need to immediately shut down the system. And then from the rocker switch, we are pulling the power to the stepper motor driver sensor board that's hidden within the housing, powering all of those components, then bringing it to a 12 volt to 5 volt step down converter. And then from there, the 5 volt power is going to the control panel and the display panel boards and powering each component there. So after all of the power was wired up and connected, we took in for each component, we added 1 or 2 wires for like the stepper motor drivers that will connect from the board to the Arduino. And then that is so that you can actually control what you're doing with the code. And Daniel is going to discuss the code.
Okay, so when the rocker switch is turned on, the LCD display, if you could go to the next slide, please. So the LCD display in the picture, it will turn on to automatically display the screen with the shaking pattern selection. And the top middle button, so in the top left picture, that middle button serves as a toggle button. So it allows the customer to switch between the screens displaying each shaker pattern. And the right button serves as a select button. So for example, if the customer wants to run an orbital shaking pattern, the toggle button could be pressed to display the appropriate pattern on the LCD, and then the select button could be pressed. Now the following screen allows the customer to set the RPM that they want for the motor to run with the dial, which with the dial, we could change it between 0 and 350 RPM. And then once selected, the duration could also be set for the motor to run with the dial as well, which we made it so it ranges from a minimum of an hour to a maximum of like 2 weeks. And when the select button was, so when the select button was pressed during this entire process, all the parameters set before were saved. So the time and the RPM. So when the final screen basically serves as, it displays all the parameters, the shaking pattern, the RPM, the duration, as a means of asking if like these parameters are correct. Now the top leftmost button serves as a cancel button. So in case the parameters weren't inputted correctly, or maybe a wrong value was accidentally selected, the customer could press the button and all the parameters will be reset, and the LCD display will go back to the very first screen with the shaking pattern selection. And if everything's correct, the select button is pressed and then the appropriate motor will run depending on the shaking pattern that was selected initially. And in addition, the green LED light will also turn on as an indication that the motors are running. Now on to Cameron to talk about the code.
So the way it's gonna start is when the rocker switch is engaged, the proximity sensors, as you can see, there are 2 of them, one for each motor. And how it's gonna work is there's a while loop that runs that moves the motors to a specific position that will serve as like the homing position of the 2 motors. So that way, when you want to go inject like a substance into the well plate, it'll be in like one spot every time. So the while loop will basically tell it to keep moving to the homing position until a certain distance from the table to the sensor is reached. And each motor will move one at a time using the stepper motors, as you can see here. And then where it says sensor inserts, that's where each sensor is gonna insert into. And then once it is homed, it'll go, the LCD will turn on, and basically it'll start with what pattern you want to select, and it'll go into the selection pattern like Daniel discussed. And this is basically an example of one of the lines of code. This block you see on the screen is the code that is the loop that keeps checking the inputs of the buttons or the dial. And basically this is the code that basically checks whether or not a button is pressed or not, or it reads the input pins on the Arduino to see whether it is pressed or not. And then so after the whole selection process, the motors will start running, and another thing that will be implemented is fail safe. So if for some reason the proximity sensors or the homing didn't like work as intended, it won't run. The motors will not start running until it is properly homed. And another thing that'll be implemented is if for some reason the motors are like not moving correctly, we'll be checking the sensors. We'll be using the sensors to check whether or not it is, if it's like getting too close to the sensors or something, and then that'll automatically shut it off, as that is a good indication of something like a problem has occurred with the motors and like how much they're turning. So yeah, that'll be implemented. And then another thing is an error will be present on the screen. So if something like that occurs, it'll inform the user that something has occurred. And then of course it'll reset back to the start screen if that occurs. And of course, and there's also a soft stop on the board as well if you want to manually stop it for any reason like emergency or something like that. And then once you stop it, you hit the cancel button that Daniel talked about, and it'll reset back to the start, selecting a pattern.
As you can see from our cost overview, the prototype is quite costly. This is mostly due to McMaster selling most items in bulk only, and bulk ordering items not from McMaster reduced our OTS part cost by roughly 20%. The raw material and manufacturing is also cheaper with production since we can bulk order material and manufacture multiple parts simultaneously. The manufacturing cost was calculated by multiplying the number of manufacturing processes by the cost of each process. If you notice, the assembly cost is not included since this assembly is designed to be assembled with very simple hand tools that most people should have and should take much less than an hour to assemble. Very similarly, the energy consumption cost was also not included because it was calculated to be much less than any other cost, and it is not an important cost to be concerned about with this design. For future improvements to this design, one of the main concerns that we had was the amount of vibration and how much the assembly would sort of wobble in place. Through some more research, we found a cheaper rail with slightly wider base, and that would provide more space and stability needed for all three types of motion. Currently,
sorry to butt in, Chase. I think.
Yeah, go ahead.
Sam, if you want to take over this part first, because the future improvements is right after this.
Yeah, sure. So I'm going to get into the design evolution for our system. So first, the well plate enclosure, which was Eli got into on the first render slide. Basically, we had to widen pretty much all of our 3D printed parts, we had to widen or shrink depending on expansion or contraction variability through 3D printing. So that was widened. The holes were flipped for actually gripping the plate itself. So we had to change hole pattern around. And we also changed our clamping mechanism. First, we used just large washers with the wing nuts, and then we transitioned to a full clamp to provide more even pressure along the well plate and the test tube rack. So the test tube rack also had a change. You can see it on the right. The first version, second version, both were 3D printed. Initially, we had walls going across the entire length, and we had to modify that since our clamping mechanism produced an interference. We needed more space, on the bottom portion of the test tube rack to clamp. And secondly, the base was thickened. Our well plate holder is designed to include an ODFI if needed. We have a spacer in there made of a polycarbonate sheet. Due to that, difference in thickness between the holder and the sheet, we needed a larger, kind of variable range for clamping our tolerance stack up. So that was also increased. It can hold 3 large test tubes, 4 smaller test tubes. And next we have the UI enclosure. So the UI enclosure is also 3D printed. We had to make some changes according to the design changes with perf board. So we had a different number of perf boards, and we had some protruding components or not protruding components over time. And we have our final iteration now with the three boards LCD display, or the 2 boards LCD display, rocker switch, and the UI controls. And lastly, for this slide, are the motion systems. So our motion, kind of ideation is very similar. Once we started manufacturing and practice, there's some things we had to address. First is an updated shoulder bolt size. So initially, the threads of our shoulder bolts were short. We were afraid that they would shear in our material. So we extended those, got a longer thread length, and also the shoulder length of the shoulder bolt was a little too large initially. So we shrunk those down, and there can be some rattle at times inside of our sleeve bearing casings, but it's not as bad as it was before. Additionally, we added PTFE tape on our joints for the linear, attaching the linear crank arm to the rod end. So that was to also minimize noise and vibration, did it pretty well. And lastly, we had an issue with our orbital plate. Initially, it was manufactured, on a mill, or I guess it was water jet, and then it was tapped in a mill, and our threads were offset in alternating directions. So this system requires a pretty tight tolerance for the angle of those threads. They need to be orthogonal, since we have a circle that's tangent to 3 points. And due to that, we had to get it remanufactured and CNC'd on an alternate pattern by flipping it over. So that was also part of our design solution. Okay, last two items, we have the shaker skirt and the perf boards. So the shaker skirt was implemented a little bit later in our process. We wanted to wait and see what our center requirements were after we got our basic motion down, those sorts of things. So it's broken into 4 pieces that are nearly identical. They're all 3D printed. So it serves a function to, like Moises said, protect the user from pinch points, and to set the sensor locations, variable heights. So the locations for the sensors were kind of changed over time based off of testing, and the attachment hole locations had to account for a couple of interferences between the base plate and rubber feed and the fastener used to clamp all of that together, and some other minor 3D printing modifications too. Lastly, perf boards. We added a third board so the screen and the buttons can all fit inside on the UI enclosure. We also added an e-stop, so a hard on-off switch circuit breaker for to immediately cut power to our motors. Initially, we coded in an e-stop and consulted with TAs. They said that we needed hard power cutoff, so that's what we included. We also added our sensors kind of retroactively. It took some time for us to determine the best sensors for our system, since we have 2 variable heights, one homing position that is linear and one that is orbital. So we settled on 2 time-of-flight sensors. And lastly, we changed the button layout according to the limited inputs and outputs on our microcontroller.
So like I was saying earlier, one of our main concerns with this was the amount of vibration and how much the assembly would wobble in place. After some research near the end of the project, we did find a cheaper rail that would save us some money, and it had a wider base, so it would supply more space, more stability for all these 3 types of motion. Currently, in our design, we have metal spacers that are used in the orbital motion, and they create a lot of noise. If we were to use plastic spacers, that would reduce the noise and would be cheaper to manufacture. We could also implement bearings by drilling holes in the orbital subassembly and have the bearing flush in the orbital plate, which would remove the need for the bushings we currently have. The dog bone linkages we have could be replaced with shorter solid linkages that would require less precision for manufacturing, but it would also increase the stability and rigidity for the orbital motion. For the electronic section, there were multiple perf boards. They all had connecting wires. They would often break due to constant handling and use. To mitigate this, the LCD screen should be seated to the motor sensor perf board, which would reduce the size of the UI enclosure. We would also need to have more solder rails that could be implemented to reduce the number of wires, and that could reduce the number of wires, so there would be less maintenance and less troubleshooting.
And then I guess just to add on a last note on specifically on the linear rail, the linear rail was one of the highest cost items in for our OTS parts. I think it was we basically bought the cheapest rail that we could find at the time, which was the rail and the two carriage blocks were, I want to say, total around $70 to $80 on McMaster car. When on Amazon there was the wider base cheaper rail that we learned about, that we could switch it and save around $60 off of our final design cost, which would also eliminate the need for those expensive rails. And in addition, we could take the rail, put two side by side, and then offset those carriage blocks instead of having them on that single rail and widening that base through that method, or through just the wider single rail, would greatly increase the stability for that orbital motion.
If I can add one more thing, Ayla, too, a big future improvement that we need that's not really addressed on the slide for the double orbital motion is that it is, at the moment, it's not homogeneous. So the way our dynamics works, which we can get into in the Q&A in a bit, basically we have one full rotation on one side and another full rotation on the other side, but from one to the other, that length, we move linearly forward and back within one full rotation, but not the other. So we haven't done testing to actually look at the agitation and see what the impact, the bias linear movement is. But an improvement to that would be to change our length on our linear motion crank arm to be slightly longer, maybe by a radius, so that the center of the arc of the circle can be compensated on both sides.
And then our last slide is just a thank you to the sponsors that are providing funding for this lab. And then also we'd like to thank all the professors and TAs that have obviously provided a great deal of input and guidance on this project. But that's it for presentation. So I guess we can start the Q&A.
Alrighty, guys. Thank you. Well done. We'll go ahead. Marilyn, I see you're the one other evaluating member still here. So if you have any questions for them, please fire away.
I don't have any questions right now. I thought you guys did a really great job.
Thank you.
Thank you.
Well then, that leaves me with questions.
Okay.
And I see the nervous smile, so you know what's coming. Actually, no, you guys did a pretty good job of explaining things. I did have one comment back when you were talking about assembly time being significantly less than an hour. Did you do the Boothroyd and Dewhurst calculations to figure out what the assembly time would be?
Chase?
Oh, we did not.
Yeah, so you kind of BS'd your way through that. You BS'd your way through that by saying, oh, it's all easily assemblable with basic hand tools and stuff, but you should still go through and tell me, even if it's going to be 40 minutes of labor, it's less than an hour of labor to assemble it, but 40 minutes is still $15 or $18 of paying a worker to come and do it. So that should still be included there. On the same note of cost, your OTS parts are very expensive, but raw material and manufacturing total are less than half of the cost of OTS parts. Are there any OTS parts that you think would be manufactured, like would be easily converted to a designed part and a manufactured part that would drop that cost down?
The manufactured parts currently are the only OTS parts that are not like electronics, are the two motors and the linear rail and the carriage and then the fasteners. I think one of the things that would help is like for some of the fastener sizes, there's like kind of a range of like different lengths for I don't know, I guess like for example, like for when we use like 540 screws, or M3 screws for our motors. I'm not I know in some instances I can't recall the exact fastener size, but there's like a few minute differences in some of them that could be like mitigated by just using one that works better for both. And that's obviously an improvement we can make. The other thing I think would be those shoulder bolts.
Yeah.
Are a pretty precise OTS part. And kind of what Chase was talking about before in the future improvement section was we could take collar bearings, seat them, and obviously the collar bearings would be a cost, but I think it'd be a lot cheaper than shoulder bolts, just because of how precise the tolerance is on the shoulder diameter. But we could seat those in both the orbital plate and the enclosure plate with pretty minimal added manufacturing time. It would kind of just be drilling a hole and using some adhesive on the outside of that, and then replacing both the actual linkages themselves, which are the most precise machined part on our design, because we need to keep everything tightly clamped or tightly bound without being clamped. Replace those flange bushings, which aren't really that expensive, but it's cost. And then we could just use like a solid linkage as well, that we could machine a lot cheaper, like what Chase was saying. And then having that be shorter would obviously help us, prevent that added momentum being thrown around as like on kind of a cantilever. So
Yeah, and also right now for our linear motion, we have rod ends with clevis mount and the binding barrel and specific side spacers and all those things. So I think we could really reduce our OTS costs there if we had, a specific cam length that could just be, casted or something.
yeah,
And that would also reduce the part complexity and the overall cost for the linear system.
I definitely think with the way that our design is set up, and we do have a lot of these like future improvements pretty heavily fleshed out. It was just, with some of like the issues with like specifically like when we wanted to incorporate, like a new rail or multiple rails onto like our orbital assembly and things of that nature, and make those changes, that it would detract from our ability to kind of like test our prototype and make sure that it was actually functional. So those were things that we wanted to do and we had fleshed out, and would be pretty easy to switch. Would we, like go back and start fresh, I guess. But just working within the scope of having to change an existing design, we weren't quite able to modify just yet. But yeah, I think we could definitely, with the rail, we could save like $60 on that. I think each one of those shoulder bolts they're expensive. They're like, I think they're like $4 or $5 each almost. They're like, they're not cheap.
You guys have some ideas for
Yeah, we could definitely drop the price, I think, right, to sit within a comfortable range.
right now, you guys are the cheapest one that I've seen so far.
Yeah, that was
So
the other thing I was gonna say is like,
So
I
I'm
know,
almost wondering what's wrong with how cheap this is, if that makes sense to you guys. Like,
I
I look
can
at how cheap it is, and I'm
explain.
like, you're half the price of the next closest team. Like,
So yeah, so when we designed it, because coming from Mech 2, one of the things that we got kind of grilled on in my presentation was the initial cost. And our Hedgehog concept for that was designing for lifetime. For that project, you had a pretty lengthy lifetime that you had to hit. And obviously not disregarding the lifetime, we've taken that into account, but the cost, I think the main facet of the cost that is differentiating us is the limits on our use of linear rails. So basically what I had planned was either swapping out that rail for the new one, which because it was cheap, we could either put in two, or taking the existing rail, splitting it in half to offset our carriage blocks by about 3/4 of an inch, which would give us a much wider base. But we really only use a single rail. And if you look at the cost of like pillow blocks, and like precision linear rail shafts, which I think a lot of groups are using, like not just for their linear, or they're maybe using a bilinear system, or they're using like multiple of these. Each of those pillow blocks costs about like $30 to $40. And those rails are like, I mean, our single 7-inch linear rail, which is just ceramic coated aluminum, was, I want to say, $20, which is, a significant cost for something that minute that a group may need multiple of. So that's kind of how we circumvented some of those costs, was in doing that.
Cool.
Yeah, without the enclosure, it's only 8 inches by 8 inches by the base plate, which is, compared to what I've seen in lab, pretty small in comparison to the footprints of other, so like, all that stuff scales as well.
Yeah, I think the size of the design definitely helped us keep things down.
Yeah. Cool. Well, in the interest of time, I think we'll go ahead and wrap up there. Thank you guys again. Job well done. Congratulations. You're done. You're free. You have survived. You've survived Mech 3. Congratulations. And yeah, great job on the presentation, and great job on explaining your thought process. And it was a very, very thorough responses to my questions. So
Thank you.
Cool. Thank you.
nicely done, guys. Congrats.